D-Branes provide a very powerful tool to describe the dynamics of gauge theories. In particular, the idea is that you describe the fields of the gauge theory in terms of the lowest modes of open strings, and in the same way, interactions are just interactions between these strings. And the nice things about this picture is that you can describe very highly non-trivial features of the gauge theory in terms of very simple objects. For example, instantons, you can think of as point-like branes, instanton, like point-like branes inside these D-Branes. And we will see that we can describe not just the standard gauge instanton, but also more exotic objects that are very appealing from the phenomenological point of view. Okay, we'll focus on local models, which are effective description. You can imagine that our world lives in some corner. There's no pointer here, no? Is this a pointer? Okay. You can imagine that we live at some corner of some Calabi-Yau compactification. This is brane stack where our gauge theory lives, and we are interested in the physics in the nearby of this singularity. Okay. Then why choose this type of models? Okay, they are simple. They are very flexible. We will see how we can describe a lot of phenomenologically interesting gauge theories in terms of these models. But they are still predictive in the sense that once you fix the geometry, everything is fixed. The field contained, interactions, and so on. Another motivation to study local models comes from ADS-CFT. The idea that any local model you can think of in terms of a dual gravity theory, which is just gravity in the background generated by this brane stack. Okay, and the nice things of this description, this dual description, is that you can describe in geometric terms highly non-trivial features of the gauge theory. For example, the gaugino condensation you can describe in terms of resolution of conical singularities, or a flowing of a gauge coupling through duality cascades you can describe in terms of just classical gravity. I will not say anything more about this holographic correspondence, but I'm sure that we will hear more during this conference. But of course, we cannot close the eyes of. This local model is a nice effective description of the physics nearby of the singularity, but there are important questions that you cannot address with them. For example, the question of modular stabilization. All my talk, I imagine that the background is fixed in some way, but at some point we should worry how string theory choose the vacuum and how you can embed these local models into a globally consistent model. This local description cannot say anything about that. Okay, the talk will be divided in two parts. In the first part, I will give an overview of D-Branes at orientifold singularities. I will very quickly go through the various options, brane intersections, orbifolds, orientifolds, and so on. This is a very basic material. I will go very quick through it, but trying to keep with me also people that are not expert on the field. Then I will describe the non-perturbative dynamics. We'll see how you can describe a gauge and exotic instanton in terms of D-Branes, and how you can use to generate a superpotential of the Affleck-Young and Seibert type, or even exotic mass and Yukawa terms. Finally, I will describe some simple instance of supersymmetry breaking mechanism. For example, I will focus on dynamical supersymmetry breaking. I will focus in dynamical supersymmetry breaking. I will present two examples of models in which supersymmetry is breaking by the generation of a gauge or exotic superpotential. Okay, the part two, Sebastián Franco will discuss the generalization of this idea to singularities of non-orbifold type. In particular, he will introduce what is called as the dimer formalis, which is a very elegant description of the general case of a gauge theory at a singularity. And he will present a longer list of models with supersymmetry breaking, for example, model exhibiting a metastable vacua or dynamical supersymmetry breaking. Okay, we start. Okay, we start. In order to fix a brane model, you should fix two ingredients. The first is the geometry. And the second is the brane configuration. What means by the geometry? The geometry means you should fix what is the metric, in which background you are. For example, we will take just orbifold singularities. Therefore, we will consider a metric of this type, Minkowski times C3 over Zn, where the orbifold is just a rotation of the internal coordinate. Xi are the internal coordinates in C3. And the orbifold is characterized by three integers. We say how you rotate eigenvalues, let's say, respect to Zn. And I will focus on supersymmetric orbifold, which means that these three integers should sum to 0. Therefore, I have two independent parameters. Oh my God. Okay, once you fix the geometry, once you fix the geometry, you should then decide what is the brane you will put in this geometry. There are several choices. For example, you can consider branes at angles, okay, or branes inside another branes, or branes with magnetic fluxes. And all these choices are completely equivalent. The only important for a brane is the difference between the boundary condition at the two ends of the open strings. This is the only important, and this is characterized by three integers again, theta I, which denote the relative boundary condition between one end of the open string and the second end. Therefore, I will call sometimes this theta twist, sometimes angles, but all this is the same. Okay. Then once you fix this, again, supersymmetry restrict the choice of thetas. For example, supersymmetry say that the sum of theta is equal to 0. I should say that every time I say 0, for example, here 0 means 0 mod n, okay, and here 0 means 0 mod integers, because theta is defined up to achieved by an integer. Okay, what type of gauge theory I can cook with this? For example, I can cook any type of supersymmetry. For example, I will always use the n=1 language. This means that I will always collect all my fields in terms of vector multiplets or chiral multiplets of n=1. For example, if I have an n=2 theory, I will take the vector and I will call vector plus a chiral in terms of n=1. And hyper for me will be chiral plus antichiral. And n=4 will be just vector plus 3 chirals. Okay? And the number of supersymmetry depend on the number of thetas which are different from 0. For example, if you take all the thetas, all the twists to 0, means the branes are parallel, you have n=4. And this is the case of D3, D3. This will always be our starting point. Then if you have two thetas which are different from 0, you have n=2. This means that the open string connecting these two branes will transform as a hypermultiplet in the bifundamental. And this is the case of D3, D7. For example, you take a D3 branes and D7, you have two planes in which the open strings have different boundaries condition. Or also D-1, D3, which is will enter in the discussion of instanton. Remember again, the only important thing is the relative angle. Therefore, D3, D7 and D-1, D3, from the point of view of the spectrum, is the same thing. Then if you take the three thetas different from 0, you get n=1, and this you can realize, for example, in context of intersecting the 7 branes. And you can go ahead. For example, you could consider even 4 thetas different from 0. Imagine a system D-1, D7, in which you have 4 planes, 4 complex planes, in which the string is twisted. Of course, this will break supersymmetry. This will have, I call n=1/2 in the sense that you have 2 superchargers. Okay, half of the supersymmetries of n=1. And this will be relevant for the discussion of exotic instantons. We will come back to this. But I just want to stress that in this case, you have just a single fermion. The idea is that always the Ramon ground state is massless. Therefore, this state you will always have. And this is the case. Okay, then the simplest gauge theory you can cook with this is like, imagine you have a system of D3, D7, ND3 and MD7 branes. Okay, then you will have two types of strings. The strings that go between the 3 and the 3, this will come in n = 4 multiples because they are parallel, D3, D3. Therefore, they will come a vector plus 3 chiral. And the strings that come between the D3 and the D7 will come in chiral, in hypermultiples. This means M n bar plus the complex conjugate representation. Okay, I will always start from this system to construct a more interesting cases, but I just want to stress that every time you have a brane intersection, you will have n = 4 sectors coming from open strings starting and ending on the same brane. Therefore, this n = 4 sector will contain always chiral matter in the adjoint representation. In the natural, there is no any evidence of adjoint representations. Therefore, these are not phenomenologically interesting. Therefore, we should use some orbifold to project out all these states. Okay. Therefore, I will always start from this system and just project, put in a curved space, and project in such a way that all this adjoint matter goes away. Okay, this is the type of metric the type of geometries I will consider, C3 divided by Zn. Omega is e to the 2 pi I over n. It's just the nth square root of the n root of the identity. Then this geometry, the closed string part is have two sectors, on twist and twist sectors. The on twist sector live in the full space, therefore are not localized at the singularity, are not interesting for the physics in the nearby the singularity, while the twist sector are localized at the singularity. But all this closed string background to me is fixed. I will not. I will always consider just the dynamics of open strings, and I will think of all these fields. For example, the twist field can be have a lot of scalars coming in hypermultiples and vector multiples, describing, for example, the size of the cycles at the singularity or the complex structure of the singularity and so on. All these I consider fixed and just focus on the open strings. Now, what should I do in order to put an open string in this background? The first thing I should say is how the open string transform under Zn. Okay, there are n possibilities. Okay, for example, imagine that you have Z3. Okay, a brane can either not transform or transform with e to the 2 pi I over 3 or e to the 4 pi I over 3. Therefore, there are three types of D3 branes, and I call the number of branes of each type, I call N0, N1, and N2. Okay, and the same for D7 branes, I call M0, M1, and M2. Okay, these numbers I can choose whatever number I want, and they are called the number of fractional branes, because you can imagine that in a Z3 singularity, you can imagine that this is almost a third of a brane. You can imagine in a Z3 singularity, the brane can move in a group of 3. Okay, therefore each of them cannot move, but 3 of them can move. And if, for example, the case of a regular brane means N1 equal to N2, this means that you can move directly. But if these numbers are different, the branes are stuck at the singularity. This is what they are called fractional branes. And you can think of these branes as higher dimensional branes wrapping non-trivial cycles of the singularities. But okay, this will not be relevant for my discussion here. The only point I want to say is that you can compute the spectrum of this theory, starting from the spectrum in flat space. You just decompose the number of branes, the total number of branes, in some number of brane NA with some phase. It transforms with some phase. Okay?
Why can't I move out if they are unequal? Why can't I move out just one common one, for example?
Because the
correction modular space.
Your C3 divided with Z3 means that everything should be symmetric with respect to the Z3. Therefore, if you have 3 branes, you can move everything should be symmetric. They should move in a symmetric form respect to rotations in this brane.
Move one out.
Sorry?
I can move one out.
You can move a group of 3, not only one. You can move in group of 3. For example, if this is 1, 1, 4, you can move 1 out, yeah, and leave 3 stuck at the okay. Okay. then how you find the spectrum? You just take, okay, you have two types of actions of the set of the orbifold group. One is in this Champardon index. We simply say how the branes transform. And the other transform in the space-time. For example, vectors do not transform on the rotations in set 3. The chiral multiplet transform with some phase. And the D3, D7 open string, you can see that they transform as a spinor. Therefore, for example, if you have a D7 brane along the 1-2 direction, this transform with a phase which goes like A1 plus A2 over 2. So you have these simple rules. And now, try to construct, take the spectrum of flat space I display in the last transparency, and just keep just the invariant components. For example, a vector, you should compensate. If this transforms like omega to the A, you should compensate with n bar, which transforms like omega to the minus A. And this is invariant. Okay? What this means is that the vector, which was a matrix n by n, now is a matrix that has components only in the block diagonal term. Okay? Therefore, you can always use the flat space formulas, or everything you can write in terms of the flat space. The only thing that you can do is that every time you find a vector, you put just a block diagonal matrix. The same for chiral multiplets. Chiral multiplets transform like omega to the A1. For example, for set 3, A1, all the A's are 1. This means that you will have just chiral blocks that go from the A to A plus 1. And all this you can nicely represent by this quiver diagram. So you can forget about all these formulas and just think of the quiver. The quiver is just saying the same thing. It's just saying, for example, that every arrow is a chiral multiplet. Okay? And here is saying that you have 3 arrows between n0 and n1. This is this 3. I goes from 1 to 3. n0 and n1. a1 is 1. Okay? Therefore, you have chiral multiplets in this way. 3 chiral multiplets. This was the phi 1, phi 2, phi 3 of n equal 4. It's just that now they are block of diagonal matrices. Okay? And then similar. Oh. And similar, you have for the D3, D7 open strings. Okay? For the D3, D7 open string, you have, for example, you have an open string between n0 and n1, and so on. Okay? Then the gauge group, I say, was U product of U and A, therefore you have a quiver gauge theory. And the flavor group is given by the gauge group of the D7 branes, which is product of U and A. Okay, now the next ingredient is introduce orientifold planes. Okay, till now we have we can realize just gauge theory with gauge group, unitary gauge group. But if you like to write theory with group SO or SP, you need to introduce orientifold planes. Orientifold planes are just mirrors where the open string can reflect and lose the orientation. In particular, you can think as an identification between a string going from one brane to a string entering in another brane. Or another way of seeing is you can take your quiver diagram and just identify, for example, you identify this gauge group with this gauge group. You imagine that there is a mirror here, and this, all the fields in this right side of the screen are identified with fields in the left side of the screen. Oh. Okay? For example, in particular, if, for example, if this gauge field is identified with itself, therefore I should say whether I symmetrize or antisymmetrize, and this will produce gauge group of with orthogonal or symplectic, either if you antisymmetrize or symmetrize. And this gauge group is identified with this one, therefore keep unitary. Okay? Therefore, again, you can forget about all formulas. You just look to the diagrams and you see, for example, the same for the chiral. This chiral is identified with this. Therefore, you have chiral multiplets in the bifundamental. And this chiral is identified with itself. Therefore, I should say whether I symmetrize or antisymmetrize. And this will produce antisymmetric or symmetric matter. Okay, the signs is my choice, and they are nicely characterized by 4 signs. For example, in my conventions, I call an O3 plane the one with 3 signs. Plus or minus is for symplectic or orthogonal projection, and O7 planes have 2 signs plus. Essentially, this sign says how many Neumann or Dirichlet boundary conditions. For example, this say that this direction, these are the 3 complex direction. This means that they are all Dirichlet. This is O3 plane. While this say is O7 plane because you have 1 Dirichlet boundary condition. Okay, but for the moment, these are just 4 signs. You should specify just together with what is the identification. You should specify 4 signs. And again, you should not care about these formulas. Everything, all the spectrum, you can read directly from here. You will have vectors in the either orthogonal, symplectic, or unitary gauge group, and by fundamental, antisymmetric, or symmetric matter, depending on those signs you are choosing. Okay. I should stress that all these gauge theories are chiral. Therefore, in principle, they are all anomalous. They make no sense. Therefore, we should impose a restriction. In such a way, we should impose the cancellation of anomalies, or equivalent, you can impose the cancellation of twist tadpole. Anomalies are directly related to twist tadpoles. Here I write the equation of anomaly, but again, this equation you can read directly from the diagram. For example, IAB is just the number of arrows between the D-Brane of type A and the D-Brane of type B. JAB is just a number, it's just intersection numbers. You have a D-Branes wrapping various cycles of the singularity, and these I are just saying what are the intersection numbers between these cycles. Okay, J is the number of arrows between a D-Brane of type A and a D7 branes of type B. Remember, D7 branes are the squares, and D-Branes are the circles. And finally, Ka is the number of branes between the D3 brane and the image. Okay? Then all these numbers are codified in this diagram, and you should just compute this. For example, let's consider again our favorite example, C3, sorry, there is a misprint here, C3 over Z3. Then let's suppose, for example, I choose orthogonal projection. I will have SON gauge group times UN gauge group coming from here. There is a consistent constraint that say that every time I have a P branes and project with group orthogonal, a P plus 4 or P minus 4 should be project with the opposite signs. Therefore, if I take gauge group SO, then the D7 brane should be project in group SP. Okay. Apart from that, you read everything from here. You have a gauge group SO0 times UN1. Flavor group SPM0 times UM1, and okay, the chiral matters you already see from the diagram, and the important point is that you have one gauge group, one unitary gauge group. Therefore, you have one anomaly equation. For out of these 4 numbers, N01 and M01, you have 3 of them are independent. The other you can fix by anomaly. But you see already that you can produce several type of gauge theory with the matter content you want. The only important thing is that the group is made as product of unitary group, and the matter is just fundamental by fundamentals or anti-symmetric or symmetric matter. You can also read the interactions. As I said, the interaction follow directly from the interaction in flat space. The only thing that you should say, for example, this is the standard prepotential of n equal 4 gauge theory. The only thing that you should say is that this phi 1, phi 2, phi 3 now are off diagonal matrices. Okay? You take the expression from n equal 4 and replace the chiral multiples by a matrix that contains only the components n0, n1, n1, n2, and n2, n0. Okay? This is the same for the Q. The Q are coming from the D3, D7. Okay? Therefore, you have all trilinears. All these trilinears interaction are just the loops of length 3 in this diagram. For example, you have phi 1, phi 2, phi 3. Or you can have, for example, Q phi 3. Sorry, Q tilde phi 3, and this is that, and so on. Okay, this is, you can set to see, forget about this term. This is just if you want to consider also strings between D7 branes. We will not do here. Okay, that's all what I should say about the perturbative gauge theory. And now we come to maybe the most interesting part, which is the non-perturbative dynamics. Sorry, I should say that in this talk I omit the reference. All what I am presenting here is the result of contributions of several groups and people. It's almost impossible. I would stop all the time if I want to fairly cite anyone that contribute here. So I excuse for this. But there are very excellent reviews on the subject. I refer you to that for a complete list of reference, or you can contact me privately if you want to know, to have reference about a specific subject. Okay, now instant. Again, I will always start from flat space. You start from considering the D3, D7 system in flat space. Oh, sorry, the question is, what is an instanton? An instanton is a point-like solution. Therefore, in string theory, there is a natural candidate for an instanton, which is a D-1 brane. D-1 brane means a point in 10-dimensional space. Okay? And an evidence that this is the right identification comes from the fact that if you compute the action of a D-1 brane, a D-1 coupled to the C0, okay, then coupled to the axiodilaton field. Therefore, the action of D-1 is just 2 pi I tau, but this is exactly, tau is exactly the gauge coupling of a D3 brane. Therefore, this is exactly the weight of an instanton in gauge theory. Okay, this is the first indication. You can go more deep on that, and then, for example, consider, for example, the Wess-Umino couplings of D-branes. For example, consider D3 branes with a non-trivial background for F. These have two terms. One term gives just the number of D3 branes, and then the second term is proportional to the instanton number. You see, it's proportional to trace of F squared. Therefore, you see that C0, which is the field that coupled to D-1 branes, the charge is precisely the instanton number. Therefore, you can identify an instanton configuration with charge K with K D-1 branes. Okay? This identification is even more impressive if you consider the modes of these open strings connecting the D-1 to the D3 branes. In particular, for example, there are two types of modes, one coming from D3, from D-1 to D3, and one coming from D-1 to its D-1. This you can identify with the position of the D-1 branes, and this you can identify with the size or the gauge orientation of the instanton. The model space of instanton is very well known, was a construct mathematician. It goes on the name of ADHM construction. And if you look into this mathematical paper, you will find exactly the same modes. And you see that these modes satisfies a highly non-trivial constraint. And this is nothing but the D and F flatness of the gauge theory living on the D-1 brane. Therefore, you, without knowing anything about instanton or about ADHM construction, you could reproduce the result just looking to the gauge theory in this D-1 plane system. Of course, this is not the end of the story, because in string theory you can construct other point-like objects. For example, what happens if I take a D-brane which wraps entirely the internal space, but from the point of view of space-time looks like as a point. For example, consider the system E3D3, AD3. This is a Euclidean D-brane wrapping the internal space, or D-1 D7. Why not? Instead of D-1 D3. Okay, and now you can repeat the analysis I did here. For example, you can compute what is the action of this AD3 brane, and the action now is proportional to the volume wrapped by this brane. This means that the scale of this object have nothing to do with the gauge theory scale. This cannot be a gauge instant. It produces effects going with a different scale. You can go ahead and go to the charge, look to the charge, And now you see that again, for example, consider the D7, D-1 system. This is the Wess-Zumino coupling. You see that again you have the number of D7 branes, but now you have that the number of D-1 is related to the trace of f to the 4. Therefore, you can think of this D-1 as a sort of instanton in 8 dimensions. Okay? This is in the past have been studied. It's not so well understood, but they are called octonionic instanton. And the crucial point is that these instantons are very different from the gauge instanton. Another indication is that, as I said in the first transparency, the modes you have only between a D-1 and D7, you have just a fermion. Okay? This means that there is no size or gauge orientation. These are instantons that do not have size or gauge orientation. They have just positions. Therefore, they are very strange and they call exotic. In the literature, some people call stringy instanton also. I don't like this name because, as I said here, these instantons are more related to gauge theories in higher dimensions, have nothing to do with string excitations. Okay? There is nothing wrong with the name, but I just want to say that this instance you can describe already, exotic instance you can describe already at the level of supergravity. You don't need string theory. Okay, what about the singularity? Now the idea is you put the instanton in the singularity. Again, we come back to our nice C3 divided by Z3 example. And for example, you put one instanton, let's say in node A. Again, you should apply the same rules. No? You should say me how the instanton transform. For example, let's say I have an instanton transforming in the representation of the invariant of the Z group action. And again, you draw all the open strings between the instanton and all possible nodes. This will be a D-1 D7 open string, D-1 D3, and the D-1 with the D3 of the same node. Okay? You write the spectrum, and you can write also, you can compute the effect of this instanton by computing the partition function with the action of D3, D-1 D7. Okay? This is an action that you can write explicitly, and this is the integral you should do. I should say that this measure half dimension, okay? Therefore, I should put this factor lambda to the beta to compensate for that. And beta is the beta function of the gauge theory living at that particular node. Okay? In this particular case, I choose gauge group SP and 0, and then the instanton is D3 D-1, which I should project in the opposite representation. This means that this will be O1 instanton. This is a gauge instanton. This is not the famous O1 exotic instant I will describe later. It's still a gauge instanton because it's a gauge of this SP and 0 gauge theory. Okay? Then I compute this integral, and in particular this integral will contain always the position of the instanton, which are 4 positions, before x, and the supersymmetric partner. Therefore, you see this is the measure of a superpotential term. Therefore, in this way, you can compute a superpotential generated by this instanton. And you see that this comes always from dimensional analysis. Okay, this is dimension 3, therefore this should be 5 to beta minus 3. Okay, and if I should do this integral to compute whether this is 0 or not, I should compute this integral. And in order to this integral give a non-trivial result, for example, I have the fermionic interactions. Okay, I write here fermionic interaction mu 0 come from these strings here, and mu I come from mu I and mu prime. And the main condition is that the number of mu 0 should be equal to the number of mu I plus mu primes. Okay? This is the number of mu 0, which is just n0, how many strings you have here, should be equal to 3 times n1 plus m1. Okay? And this condition is just the standard condition you find if you are familiar in gauge theory for with the computation of Affleck, Dunn, and Seibert, for example. This is the condition that should satisfy a gauge theory in order to in order to be able to generate a superpotential by gauge instantons. Okay, but the nice thing is that here you find all these just counting the number of arrows between the instanton and the different branes. Okay, and another nice thing is that if you use this condition and plug in this formula for beta, you see that beta minus 3 is just the number of chiral multiples. Therefore, this superpotential is just lambda to the beta dividing by the product of chiral multiples. This just from dimensional analysis and from this counting, you already know what is the superpotential generated by the instanton. And typically, there is only one singlet you can construct in this way. For most of the case, you can completely determine the superpotential just from this simple analysis. Here I just list, just to give you a taste of what you can do, various gauge theories with instanton. The star means where the instanton sits. I should say that instantons give a contribution of this type only if you have a single instanton. Otherwise, you have too many zero modes, and you will get always zero. Okay, I go to exotic instantons. Okay, the story for exotic instanton is very similar. The only difference is that now the instanton is sitting in an empty node. Okay, you see that if here there will be some brane, this will be the instanton of that gauge theory. But now the gauge theory is SP0. Therefore, exotic instanton in this context, you could think just as gauge instanton of SP0 gauge theory. And nicely, all formulas are valid again. This formula is still valid. You just put in the SP n beta function, you put n equal to 0. You find something that you cannot interpret as the beta function. This would be like the beta function of the SP0 here. But this formula is still true. And you see that beta minus 3, this 3 minus beta is positive. Therefore, the main difference with the previous case is that now this superpotential will be polynomial. Before was lambda divided by 5 to the something, now it's 5 to the something. Okay? To compute the superpotential is even easier because the action is just quadratic in fermion. There is only, I say you that all strings connecting this d minus 1 with the D-Brane are just fermions. Therefore, you find just a quadratic action in fermions. You can integrate it and find a polynomial. You will find some polynomials of the fields. The details here are not important. I just want to stress the two main points. The two main points that this exotic instanton generate polynomial interactions, and another important point is that the interactions are generated at the scale, which is not the gauge theory scale, but is the scale of that gauge theory. Therefore, it's another scale. Okay? And this is very important because then you can create hierarchies and discuss several phenomenologically interesting features. Okay, I come to SUSY breaking. There are two ways of, sorry, how much time I have?
No, ask. You have to finish, say, at 10 past 11, but the two of you. You have 1 hour and a half, the two of you together.
1 hour and a half.
You started
45 minutes. My 45 minutes when finished?
5 minutes, in principle.
Okay, I will take 10 minutes. Okay. No, then you, sorry. Okay, there are two ways of break supersymmetry. You can break explicitly supersymmetry. We already see that you can break supersymmetry by angles. If you don't satisfy this condition, sum over the theta equal to 0, you break supersymmetry. And this, you can see, is just because the scalars of the natural sector get mass. Or you can break by, this is still explicit by introducing fluxes. For example, if you introduce a flux, you will give mass to some of the gauge genus. But the problem with this type of breaking is that it's very drastic. The theory, the Lagrangian is not supersymmetric, therefore we lose all the power of supersymmetric theory. We don't have control on the quantum corrections. And therefore I will focus on a more soft way of breaking supersymmetry, which is symmetry when supersymmetry is broken spontaneously. This means that the Lagrangian is supersymmetric, but the vacuum is not supersymmetric. Okay? And I will present two examples, one in which you have supersymmetry by gauge instanton, model, which is C3 divided by Z5. And in another example in which the supersymmetry is broken by exotic instances.
So are you assuming that there's no, I mean, these are sort of non-compact models, right? So are you assuming that there's no important effect in supersymmetry breaking coming from global effects?
This is a very important point. This is the limit of all local construction. We cannot, we assume that the background is fixed somewhere, but we don't know how. Yes. This is a very drastic assumption, but to answer this question, of course, you should go to global model to see, or at least partially, I don't know if you will discuss this in the discussion section. I think that still you can do something intermediate in which you at least try to fix the closed string moduli associated to the singularity. This still we have not tried, but I think this would be very interesting. This would be at least step towards. But of course, here I just assume I have a background which is fixed somewhere, and then just study the dynamics of open strings. Okay, then the first example is C3 divided by Z5 singularity. Okay, you just take, for example, one C3 over Z5, and I put one D-Brane here, one here, and 5 here. You can see that this satisfies all anomaly conditions. And the spectrum is given in this table. Essentially, you have 2 generations of standard model particles. This is a grand unification model. You see, you have U5, you have a 10, and the 5 bar. But you see, string theory never gives you what you exactly want. It gives something more. It gives you an extra 5 bar, an extra 5 to some scalars, and so on. Okay? This is just to say that it's true that we have a lot of freedom in choosing this singularity, but it's not completely random. I mean, we should. It's hard to find exactly. It's hard to break supersymmetry. Okay, this is the perturbative superpotential. It's just all triangles here. For example, you have CBE, BCE, this triangle here, or ACC. Okay. And you have also D terms. Essentially, the vacuum is found by simply extremizing the superpotential and the D terms. Okay? Of course, you have always the vacuum, the trivial vacuum, all the fields to 0. But you can do something more funny. You can just, for example, consider a non-trivial Fayet-Iliopoulos term in the U1 part. This is something, it's a U1 hidden. And still, you can get the supersymmetric vacuum by simply take a V1 equal to square root of C1. Therefore, this vacuum is still supersymmetric. Okay? You are just breaking an internal U1. Okay? But then when you go to the non-perturbative level, you see that this makes a difference. And here is the superpotential. This is the perturbative potential. And then you can see that this satisfies the condition I wrote for instanton before. And this is the superpotential. And if you start to compute the F-flatness condition for this superpotential, you will see that this will never satisfy. This is a famous example of supersymmetry breaking, dynamical supersymmetry breaking with 2 generations of a standard model. But you see, in string theory, it comes in a highly non-trivial way. I don't find a quiver that have just U5 with 2 generations and this superpotential. I find just after starting from a theory which is bigger, I put the Fayet-Iliopoulos, going to a strong coupling, and so on. But okay, this is the way this model breaks supersymmetry.
Where does that non-conservative, the lambda tangent, what's this coming from? What instant?
This comes from an instant. This is an instanton in the U5.
But it's a gauge theory instanton.
It's a gauge theory.
The Affleck-Dunn-Seiberg.
It's an Affleck-Dunn-Seiberg, in fact. In fact, you see it's lambda over some scalar field.
Right.
The gauge instant always generates superpotential of this type.
Is this a minimum?
Hmm?
I mean, is this a minimum of the F?
I say there is no F term. Of course, there is a minimum of the full potential. Not there is no solution of the F flatness.
Yeah, but it's a minimum. There's a non-supersymmetric minimum.
There is a non-supersymmetric minimum, yes.
But size of flat direction or something? I mean, what's fixing the size that you blow up?
You mean the supersymmetry breaking scale is given by these two parameters, m and lambda. Lambda is the scale of the gauge theory, and m is given by this Fayette-Lopez term.
Which you set by hand.
Of course, yes. This is part of the background. In fact, the theory prefers to be supersymmetric, prefers to have all the fields to 0. There is no way out.
It's somehow a local parameter, right? I mean, it's related to the local volume of your...
It's a closed string parameter. This is related to what I said before. The best point would be try to extremize respect to also these parameters. These parameters will appear also in my description. This is just an external parameter. It's a closed string parameter. But it would be nice if you can find a model in which you at least stabilize the model at the singularity. I don't
What
have.
kind of thing is it? Close string modulus is it? Size of
It's one of the twists. One of the twists. You see, one of the twist moduli.
or secondary model?
Maybe we can in that this during the discussion session, but I agree. I mean, as you know, I mean, if I remember correctly, this for this whole story to work, you really need this Fayette-Diopoulos, which should be a genuine Fayette-Diopoulos from this point of view. But we know that. I mean, I'm not aware. Maybe there has been some progress, which I don't know, of models in which you can really have this Fayette-Diopoulos not being model dependent, and therefore, I mean, it's not easy to stabilize this.
Of course, it's not easy. But I have.
These are some other assumptions that you are doing are typical, but this is a very strong assumption because I personally don't know counterexample in which concrete.
I think that's a perfect thing to do in the discussion.
Yes.
And since we are a bit running late anyway,
Okay.
Yes.
postpone it.
Okay. Very quick. What are the? In any case, it's the most interesting point in this. Okay, let me call now about the exotic instant. Like I say, string theory is very hard to break supersymmetry. This is the message of that. Okay, this case is for example, the exotic instanton. I take this example C3 divided by Z4, and I just occupy one of the nodes. For example, I just occupy this node with a U1, use a single D-Brane. In this case, I put the instanton here. This is exotic because it's in an empty node. I just have two fermionic modes. The action is just S mu1, mu2. You just integrate it, and you find a linear term. This is what is called Polanyi model. This is clearly the minimum of this. If you just vary respect to S, you see that these have no supersymmetric minimum. Therefore, this breaks supersymmetry. And since I am running out of time, I skip the summary, but I just flash. I'm sorry. Okay, this is this. Thank you.
Is it fine?
No, I think it has to be
Oh, yeah, here.
no, the best thing would be
Okay. Good. Oh, yes.
I can't see from
Yes.
this.
Don't worry. Okay, so can I start? So again, let me thank the organizers for inviting me here and allowing me to talk. So far Francisco was talking, described to us very well in the context of orbifolds, how to get gauge theories, queer gauge theories there, and the role of instantons. That was a very detailed description. So now I would like to move on and talking about tools to go beyond orbifold singularities. You know, this is in the spirit of a review, so it's going to be quite quick. Of course, we have all this beautiful time for discussions and questions, so it will be nice. So again, let me say a little, again, begin by repeating a few of the motivations that Francisco gave, why we are interested, for example, in these local models using D-Branes. I mean, of course, it gives you a local approach to string phenomenology in type 2B. We might be living at some branes at some singularities, for example, from the point of view of some questions that are relevant for particle physics, or most relevant for particle physics, H-symmetry, matter content, and superpotential. We only care about the vicinity of the brane, so we can really approach this geometry by a non-compact geometry. But of course, there are important questions that have to do with the UV completion, and we have many of them have already arisen that do care about the full compactification. I'm not going to say anything about that, but of course it's very important. Of course, these kind of configurations of branes at singularities give us new perspectives for studying quantum field theories and geometry, the relation between geometry and quantum field theory. There are the basic setups for the ADS-CFT correspondence with reduced supersymmetry or reduced symmetry, okay, in which we can describe strongly coupled quantum field theories in terms of weakly coupled gravity. So that's also a very interesting direction. And as we might see now, once you realize quantum field theories in terms of geometry, typically non-trivial quantum field theory dynamics gets geometrized, gets translated into some non-trivial geometry statements. I mean, we know a lot, for example, Klebanov-Strassler about confinement, for example, the notion of dualities, and for the purpose of today's talk, the issue of dynamical supersymmetry breaking sometimes gets translated in some geometric statement. Okay. Of course, there are other motivations for doing that. If we are interested in string phenomenology, we want to investigate all possible corners of perturbative string theory. The vacuum of the real world might be sitting away from these perturbative corners, so the more we explore all of them, the better. So it's interesting to study this one in particular. So let me say a few words about how we get quivers from geometry. And as we saw in the previous half of the talk, once you have this kind of configuration with D-Branes over some singular Calabi-Yau, the gauge theory that appears there is typically a quiver gauge theory. Okay, and the way you have to think about it is that an quiver theory is some oriented graph of this type, in which each node corresponds to some gauge symmetry group. I'm not specifying what the ranks of these symmetry groups are yet, but there are some symmetry groups or some vector multiplet associated to them in n=1 language, and there's some charge matter or some chiral multiplets transforming in bifundamental representation. Okay, we have oriented arrows here because we say, for example, that these things are transforming in the fundamental representation of the tail and the anti-fundamental representation of the gauge group at the head. Okay, on top of that, this is an n=1, typically an n=1 gauge theory, so it's not fully specified when you specify the matter content. These theories are determined by also specifying a superpotential, and the superpotential is some collection, some holomorphic function in gauge invariants. Okay, so in a quiver, I'm suppressing trace symbol here just to make it look simpler. But in quiver language, a superpotential is some collection of closed loops in the quiver. Okay, in principle, it's not every possible loop. It's some of the loops. For example, here you have one that goes from node 2 to 3 to 5 to 6 to 2 again. So this term is a closed loop here, and it really, if we really want to understand the mapping between quantum field theory and geometry and quantum field theory, we need to understand which, for example, not only how the quiver is determined, but which of these terms are, which of all the possible gauge invariant terms are there in the superpotential. Okay? And of course, we can also, if you give me the geometry, you can get a gauge theory, but if you give me the gauge theory under the assumption that I live in one of these configurations, you can determine the geometry. And the geometry, of course, the way in which the theory of D-Branes see the geometry is in terms of its moduli space. Okay, so you look at the moduli space of the gauge theory and you reconstruct the higher dimensions that you are living in. Okay, so I want to go beyond orbifolds, and of course also containing orbifolds, but I'm going to do it in a restricted class of Calabi-Yau's, which are toric Calabi-Yau's. Okay, this is an infinite class. It's very flexible. It allows you to investigate many phenomena, but it's still somehow constrained, and it will be constrained in a way that is going to be useful for us. So what is a toric variety? Well, it admits a toric variety is something that admits some U1 to the D action, or it has some kind of D-dimensional torus vibration. Okay, and one of the nice things about this kind of geometries is that they can be described in very combinatorial way by specifying how these cycles in this vibration shrinks and what's the relation between where they shrink. Okay, so let me just give you two examples of that. One example of a toric geometry is just the complex plane. So you can think about the complex plane like, you know, the argument or the distance from the origin, and then a circle on top of each point of this semi-infinite line. Okay, so this is the complex plane, and this circle is growing as you move away from the origin and shrinking to zero size at the origin. If we forget about the information concerning the size of this circle, I mean, just say where this circle degenerates, this can be represented by this semi-infinite line. So that's a pictorial way of representing this geometry. Similarly, we can have a two-sphere. Okay, so in a two-sphere, again, we can think about it as a finite segment and all the circles that go parallel to the equator in the sphere. Okay, and these circles, of course, shrink to zero size at the North Pole and the South Pole. So if we do the same kind of representation, this looks like this. The two-sphere is represented by a segment. Okay, the size of the two-sphere corresponds to the size of this segment, and of course, if you look very close to either North or South Pole, you get a picture that exactly looks like this. You get a patch that looks exactly like the complex plane. So we are going to focus here on cones that are some toric Calabi-Yau threefolds, which are toric, and they are going to be described by some graphs or some representations that go beyond this one, but they look similar to them. That are called PQ webs. Okay, you can think about these things as being just a pictorial representation of what the geometry looks like. Okay, it's called PQ because there are two integers numbers that label each of these external legs, and that they determine the slope, and you can think about them in exactly the same way that we thought about this diagram. Every finite segment, or every segment here, corresponds to some kind of a two-cycle or a two-sphere. There's going to be a T2 fiber over this plane, so this whole thing is some four-cycle. The T2, one of the circles in the T2 degenerates to zero size over the segments. That's why you get the two-sphere, and all the cycles degenerate when you get the intersection of two lines. Okay, and I mean, if you look at the articles, or if you look at these things, it's also useful sometimes to describe the geometry in terms of the dual graph of this, where you replace each of these faces by a point. This so-called toric diagram. Okay, some collection of points that tells you more or less what the geometry is. So here you see more or less that there's a compact four cycle here. Then you see how many two cycles there are there, and so on. Okay, so now that we specify this class of theories, let me say a few more words, which is non-generic. Let me say a few more words about what the gauge theory looks like there. Okay? So we are going to look at this kind of configuration, which was the configuration I mentioned at the beginning, but in the specific case in which this cone is toric. And this, as I said, this constraint structure maps into a constraint structure for the quantum field theories. Okay, and what happens is that these gauge theories have F-term equations that are of the following form: are the form of the monomials equal to some other monomial. Okay, so as you see, I mean, the restriction is in terms of the superpotential. If you recall what an F-term is, Okay, it's just the derivative. Well, it's related to the derivative of the superpotential with respect to the chiral superfields. So the fact that this equation, the vanishing of the F term, is equal to a monomial equal to another monomial, means that the superpotential is some polynomial, and every chiral field in the gauge theory appears exactly in two terms. And for the purpose of the combinatorics, I will say that it appears in two terms with opposite signs. Of course, they have complex coefficients, but that's what we are going to say today. Okay, so now let me go to Brane tiles or dimer models, which are the tools that I'm going to use to describe these things. So, as I said, these are gauge, this n equals to 1 gauge theories. In order to fully specify them, you have to tell me what the gauge theory, what the quiver is, and what the superpotential is. Okay, and further I said that in the class of theories that I'm going to study, this superpotential has some very special structure. In this structure in which that determines that every chiral field appears exactly in two superpotential terms. Okay, so now let me just introduce a new object that combines the information in the quiver and the information in the superpotential. Okay, so far it's just a rewriting of all the information that we know about the gauge theory. It's a graphical. If you're interested in graphically representing this information, that's one of the things that you can do. It will become clear later that it's a useful thing to do. Okay, but so far it's just a rewriting, re-encoding of the same information that we have. Okay, and the object that does this job is called a periodic quiver. Okay, and it's a quiver that lives on a surface of a two-dimensional torus, such that every superpotential is really encoded in a plaquette or minimal loop into this graph. So let me show you an example. Okay, so this is an example of a gauge theory that arises when you put branes on a C2 orbifold of a conifold. Yeah, as you might expect from the being an orbifold of a conifold, it has a C2 orbifold of a conifold. It has 4 gauge groups, so it's double the number of gauge groups in the conifold. Of course, in order for this to be more instructive, I picked not the obvious one that you would obtain by orbifolding the known theory of the conifold. That's fine, and it has 12 chiral multiplets. Okay, here this means that there are 4 arrows sitting here, 4 bifundamentals here, 2 here, 2 here, 2 here, and 2 here. And in principle, for example, you could form 16 cubic couplings here, 16 cubic couplings, a total of 32 at the very least superpotential terms. But the superpotential of this theory, as determined from geometry, only has 12 of them. Okay, 8 of them. Okay, so the notation here is that subindices correspond to the names of the gauge groups. These arrows are connecting, and the superindices are just names for different fields that corresponds to some SU2 times SU2 global symmetry that this theory has. Okay, so now let me try to combine these two pieces of information into a single object. And it looks like this. I just put here many copies of them. But now this is such that what I did is that every single term here appears as a little oriented plaquette here. Okay, so for example, and there's a unit cell. Of course, there's a unit cell that you can copy and tile the entire plane. It's a 2 torus. That's because this direction is oriented, this edge is identified with this one, and the same here. You can check that inside the unit cell you have exactly the amount of information that you have here. You have, if you look, the total of 4 gauge groups. You have the 12 chiral multiplets, and you have 8 little plaquettes here, 8 little triangles, which are these 8 superpotential terms. So, for example, this is one of the terms in the superpotential. Goes 1, 3, 2, and then 1, 1, 3, 2, 1, and here it's represented by this plaquette. Similarly, you can have another plaquette, and it's represented by this. This term is represented by this plaquette. And as you can see, this is the original constraint that I told you this theory satisfies, is that every bifundamental appears, or every chiral multiplet appears in exactly 2 superpotential terms. For example, this one in red, x1311, appears exactly in these 2 and nothing else. And here you see how this has been encoded. Okay, this is the only common edge that appears at the intersection of these 2 plaquettes. Okay, so by construction, this kind of object already implements this condition. But so far, I'm just rewriting it in a fancy graphical way. We are going to see that it's useful, but we are going to see that it's useful later. Okay, and let's look closely at these 2 plaquettes, the 2 plaquettes that involve a common edge, and let's look at what the F term looks like. So the F term associated to this field corresponds to the derivative of these 2 things with respect to this field, and it just tells you that the 2 sides, the opposite sides of the plaquette, have to be equal. Okay, so that's how the F term equations appear here, and we are going to revisit this situation later. Yes.
So for any toric, for any QURE, you can write a periodic QURE, so it's 1-to-1 correspondence. So
sorry?
there is 1-to-1 correspondence between this QURE and this QURE, the periodic one.
Yeah, because once you give me this, you can go around and construct this object. If you give me the 2 things. Okay. There's no 1-to-1 correspondence between geometry and the
No, between the 2 QURE.
Yeah. Because, this is just telling you how to glue things. You start from whatever plaquette you want, and you start looking at the chiral multiplets. You look at which term contains the edges in that plaquette, so you construct the other plaquettes. And you go that until you cover enough space to pick your unit cell. Okay? And of course, the 2 directions of the unit cell have to do with a pair of U1 isometries that this toric thing has. It has a U1 cube. 2 of them are already encapsulated here. Okay, so far we saw the periodic quiver look like this for our example. Okay, and so what's a brane tiling? Again, a brane tiling is so far a usual pictorial way of telling you what the gauge theory is, just that, or if you tell me what the gauge theory is, I can construct this object, and it's a dual graph. And the dual graph in the sense that I take every face or every plaquette and replace it by a node. I take every node and replace it by a face, and I take every edge and I replace it by a transverse edge. Fancy. And you can eliminate the underlying quiver and it looks like this. And again, there's a unit cell. Okay, so good. One of the things that you can see is that this graph is what's called bipartite. I mean, it contains, it's like a lattice made out of 2 types of atoms, that you can call it black and white. And, it's white nodes and only connected to black nodes, and black nodes are only connected to white nodes. And you can trace that back to the quiver. It has to do with the orientation of the plaquettes. One color corresponds to clockwise orientation, and the other one corresponds to counterclockwise. And you cannot have adjacent things with the same orientation. And has to do with chirality. And this is what I would call a brane tiling or a dimer model. I will use the 2 things as a synonym. Okay. One important thing, so far this is just a graph. It's just telling you a gauge theory, and I will give you the dictionary for the gauge theory. But it's important to say that in string theory, these things are physical configurations of branes that are dual to the branes at the singularity. If you want, these are kind of generalized Hanani-Witten setups, in which this is really representing some system of NS5 branes, which are encoded in this lattice, and some D5 branes, which are encoded are living on the plane. Okay, so at low energies, this thing is finite in these 2 directions. It gives you a 4-dimensional gauge theory. Okay, so how do we see the gauge theory here? Well, a U1 gauge group corresponding to the node in the quiver, so it corresponds to a face here. Bifundamental or adjoint chiral multiplets corresponds to edges here, because they are the duals to arrows. and superpotential terms correspond to these plaquettes in the quiver, in the periodic quiver, and these are the nodes here. Okay, so if we now use this dictionary and we look at this theory, we see that in the unit cell we have 4 phases, which were the 4 gauge groups of the original quiver that I'm discussing as an example. You see that you have 8 plus 2 plus 2. You have a total of 12 edges, which are the 12 chiral multiplets, and you have a total of 8 nodes. Okay, all of them have valence 3, which are the 8 cubic terms in the superpotential. Okay, so it's just, so far we have just rewritten this thing. So before telling you why this is useful, let me introduce one object that some of you might have heard me saying it many times, but you know, this is a typical object which is very useful in investigating this kind of graphs from a combinatorial point of view. So it will become clear why it's useful later. And it's called a perfect matching. Okay, a perfect matching is a configuration of edges that such that every vertex in the graph is an endpoint of precisely one edge. Okay, so here is the unit cell of the graph I'm discussing so far, and the edges in the perfect matching are shown in red, you know, and every node is exactly the endpoint of one red edge. Okay? So that's the definition. You can also say that, I don't know, every node is in some kind of monogamous relationship. And these things are also, since it's very fashionable, this is also, to mention something in condensed matter physics, this is also something that people investigate when, for example, discussing spins on lattices. Okay, so if you want to form some lowest energy configuration by pairing nearest neighbors to form something with zero net spin, this is called a resonating valence bond phase. And so, just to give you a fancy name, but you know, in this example, this is not the only perfect matching. There are 8 more perfect matches. Okay, there are 9 perfect matches. And in this case, we can go around and find them just by, you know, using the definition and looking for what are the configurations that do the job. Okay. There exist very powerful tools for determining these objects, so that's why these things are interesting. Okay, and I will say a few words about how to find them in general. And you can see that for any of these configurations, you can associate a couple of integers, okay, which is the number of times and you can define it in many ways, and one possible way of defining them is by looking at the number of times you have the number of edges that cross the unit cell in each of the 2 directions with orientation. By linear orientation, meaning saying that, for example, if you come from a white node, you have a +1, and if you come from a black node, you have a -1. So, for example, this guy doesn't have any crossing, so I would say it's 0, 0. This guy has 1 crossing in the horizontal direction coming from the white, I would say it's a 1, 0. And this guy has a 1 crossing in the vertical direction coming from white, I would say it's 0, 1. But you can do similar exercise for all of them. Okay, so all of these guys naturally fit into some set 2 lattice. Okay, any questions so far? Okay, so what I'm going to show you in the next slides that why was it useful to translate the gauge theory into this graphical language is because it will give me a useful way of solving for the moduli space, which is what I told you is the way in which if you give me the quantum field theory, you get what the geometry was. Of course, it will be much more than that, and I'm not going to discuss it today, but it's also possible. These things make it possible to go from geometry to quantum field theory, but just let me say that. Okay. So why perfect matchings were even mentioned here? I will tell you that this is because they can solve the F-term equations very easily. Okay, and this was the most difficult part of solving for the moduli space of these quantum field theories, or at least solving them in a useful way. It was difficult. Okay, so for any arrow in the quiver, I told you that any chiral superfield appears in exactly two terms in the superpotential with opposite signs. So we know that the superpotential given an arrow x0 looks like this. There are several terms that don't involve f0, x0, and there are two terms that involve it, and it will be some product of x0 with some monomial, which I call p1, and another one which is x0 times some other monomial. Okay, these are all the terms in the superpotential in which x0 appears. There's nothing else. First, then you have to go over all the possible chiral superfields. And the f terms for x0 just looks like this. It's just the equality between the two monomials x0 is coupled to. That's the only thing that you have to solve. And you have to solve this for all the possible chiral superfields in your theory and parameterize it in a useful way that allows you to describe the toric geometry. So this is what the dimer models do for you. So graphically, you look at a piece of the graph, and the only piece of the graph that involves these chiral multiplets looks like this. It can have any valence on each of the two sides, okay? And this collection of edges on the left corresponds to what I call the monomial p1. This collection of edges on the right, or the product of these edges, corresponds to the monomial p2. This is a superpotential term. This is another superpotential term. And vanishing of the f terms just says that graphically means that the left hand side has to be equal to the right hand side. Okay, so this is the equation that you have to solve. Okay, so now let me say why perfect matchings were useful. Okay, so we can solve these equations, but let's consider the following map. Let me say that I'm going to use the perfect matchings, which I call p mu, as my new variables, and I'm going to say that every x is the product of all the perfect matchings that contain x. Okay, so remember, a chiral superfield was an edge in the graph, and I will say that an edge is replaced by some ansatz, which is just the product of the perfect matchings that contain that edge. Okay, because this exponent can be either 0 or 1 depending on whether the edge is in the perfect matching. Okay, so now let's try to look at how these equations look like. And you have the first monomial has to be equal to the second monomial. The first monomial is the product of all the chiral fields in the monomial, and I take each chiral field and I replace it by the product of the perfect matchings in it. Okay, so now in order for this equation to be true, every perfect matching that appears here should appear on the right hand side. Okay, so there are two possibilities. If a perfect matching contains the edge in the middle, it doesn't appear in any of the two sides, so that this guy is not here. But if a perfect matching appears on the left, okay, just due to the definition of the perfect matchings is that every node has to appear in one edge in the perfect matching, it will appear on the right. Okay, so this tells you that perfect matchings automatically solve off the term equation. So this is why these guys are useful for determining the geometry. So you can think about these things as what you would call the gauge linear sigma model fields for the toric geometry. And by doing this, it takes something that was originally complicated, which was finding the geometry for the moduli space of these quantum field theories and describing in terms of toric geometry, into a trivial problem, which is just finding these perfect matchings. And it's really trivial because it's very easy to find the perfect matchings. I mean, I gave you an example in which I did it by hand, but there's an automatic way of doing it, and corresponds just to computing some determinant of some adjacency matrix. Okay, I won't go into the details, but you can construct some adjacency matrix of the graph, where here you have the white nodes and here you have the black nodes as rows, and the determinant of this object automatically spits out something in which it will be some polynomial in two variables. The exponents in these two variables are these two integers that I associated to each of these perfect matchings, and the coefficients are really the perfect matchings. Okay, so it's an automatic technology. Okay, and the positions or the exponents that appear here are really the positions of these objects in the toric diagram. Okay, so if I do this exercise for the example that I was showing, remember that there were 9 perfect matchings. Here you have 5 that sit on the middle, 4 additional ones that sit on the corners. The toric diagram looks like this. It's something that has a 4th cycle, and if you know what the toric diagram of the conifold is, this is some refinement of the toric diagram of the conifold, which is the way in which an orbifold shows up in this language. Okay? Any question?
If I give now a toric diagram, it's automatically to reproduce the QV diagram.
Sorry?
If I now give you a toric diagram, and before the procedure was long and
Then
complex,
I didn't explain how to go back, but there's a procedure to tell me what a dimer model is. I mean, you know, it's not unique. There will be dualities here. Okay?
but this all this ambiguity is swallowed in. How do you get many QV diagrams out of one toric diagram?
Well, the procedure involves some degree of freedom, which corresponds to some motion of some
It's
sort.
inside the definition of the perfect matchings. Or
Well, the perfect matches are useful to go from one to the other. I mean, from going back, I won't use perfect matchings. Okay? Yes. I mean, the perfect matches are defined in terms of a graph, so meaning it means that it's in terms of one of the gauge theories. If I take any of the gauge theories which are dual to this object, I will obtain the same toric diagram. Okay? So, this I think it's the end of what I want to say about these dimer models, but let me say a few words just to summarize. You know, I think that dimer models give you the largest classification of 4-dimensional n equals 1 superconformal field theories that we know. I mean, things that are purely n equals to 1, not things that come from n equals to 2, and so on, and connect them to their gravity duals. And this has been used for finding infinite classes of ADS-CFT, explicit dual pairs. Okay, they can be extended. These techniques can be extended to adding flavor branes and orientifolds of these geometries. I mean, this is some like extension of what Francisco was discussing. I mean, they have been applied very successfully to local model building. I mean, probably some of the people are here. I mean, there are some very nice examples of using these techniques to get things like the standard model with a nice CKM and leptonic missing matrix. You know, of course, it doesn't tell you that this is the only construction, but it's a proof of principle that you can accommodate these kind of structures into geometry. And of course, it's related to many other directions like mirror symmetry, cluster algebras, crystal melting, integrable systems. Okay, so now let me switch to supersymmetry breaking. Okay. Okay. So probably I'm going to. So the thing that I want to do now is, you know, I want to go over a set. I mean, not with no specific reason to choose them. List of supersymmetry breaking models that can appear in these local constructions. Okay. I mean, this has been going on over several years, and I think that it's very useful for the purpose of a workshop like this to just look at all of them again together. Maybe it can spark some idea. And also the purpose of this choice, which is, I mean, as I say, it's not exhaustive, is to give you an idea of what's the wide range of things that can appear in this context. Okay. So let me start from the beginning. And you know, this is string theory, very complicated thing, but one of the things that I think it's important to emphasize is that even the simplest textbook models of supersymmetry breaking can be realized here. I mean, you don't need fancy dynamical supersymmetry breaking. You can just obtain what's we call retrofitted version of the simplest textbook models. Okay, and in order for, I mean, you can do this in terms of many geometries, but I think that a very nice laboratory or platform for obtaining many of these things is in terms of what's called some non-chiral orbifolds of the conifold. I mean, why it's interesting, because why it's a very useful place, because, you know, these theories are generically, I mean, the theories that you obtain in these D-Branes are generically chiral. You start to have to worry about, if you want to play with the fractional branes in them, you have to start worrying about tadpole cancellation or anomaly cancellation. If you start from a non-chiral theory, there are no anomalies there, so there's more freedom in choosing these gauge groups. Okay, so this is, for example, how the kind of orbifolds I'm looking at will look for C3 orbifold of the conifold. There are 2 arrows in each direction, and there are quartic couplings for the inherited from the conifold for each corner. Okay. Okay, and I will come back to these examples also later because they are the nice laboratory. And these things are dual to Hanani-Witten type configurations in type 2A, in terms of rotated NS branes and D4 branes, so they're very easy to visualize. And as Francisco said, fractional branes corresponds to anomaly-free rank assignments of the gauge groups. Of course, tadpole cancellation is more constraining than just anomaly cancellation. It's slightly more subtle, but at least you have to pass this constraint. Okay, and if you start from this configuration and you start doing cyber dualities, or if you start from this configuration and you start moving the NS5 branes around, there are only 2 types of nodes that you can have locally in the quiver. Okay, there's the type of node that I already showed there, which are one node which has just 2 arrows coming in, 2 arrows coming out, and there will be a quartic superpotential term corresponding to the 4 arrows that connect to it. And if you dualize some of the nodes, you can come up with this kind of configuration, which is something, this is like a conifold-like node, and this is like an n equals to 2 like node. It has an adjoint now, and there are cubic couplings much like in n equals to 2 gauge theory, coupling this node to a pair of fundamentals on each side. Okay, so this is like a useful set of building blocks that we can use. And these people here, Aronik, Kachu, and Silverstein, were the ones that used these things to construct this simple model. So let me say how it works. Okay, so the general strategy is to consider some wrapped D-Brane instanton on one of the empty nodes, much like Francisco did, and orientifold this node in order to get rid of these zero modes, these extra fermionic zero modes that you don't want, in order to be able to generate a non-vanishing contribution to the superpotential. Okay, so now, how can I construct a Polanyi? Well, Polanyi model is in this big quiver. I just occupy one of these nodes that has an adjoint. I orientifold the one next to it. The fermionic zero modes are the things that I'm showing in red, have the same kind of couplings that the space-filling branes would have to this adjoint. And once you integrate the fermionic zero modes, you get just the determinant of the guy these guys were coupled to, which is this guy X. So you get a superpotential term that is the Polanyi model. Okay. So how do you construct a Fayette model? Well, you look at a conifold-like piece of the quiver. You put an instanton here on the next node. These are the fermionic zero modes. The superpotential will be like a mass term for x23 and x32. There are 2 U1 symmetries. These are the occupation numbers for each of the nodes. There are 2 U1 symmetries here. Everything is neutral under the sum of them. They're not neutral under the difference. If you allow me, and this is the only case in which I will do, to turn on Fi term for this thing, you get the Fayette model. You get supersymmetry breaking by the incompatibility of this Fi term and the masses for the chiral multiplets.
You write lambda 1, but I guess it is the scale greater to the 0.
Yeah, I call it lambda 1, and it's seeing some scale associated to this node.
Yeah, well,
But what do you want?
okay, yes.
And I put it to the right power.
It's a 1 also underneath.
Okay.
No, but
The one is this one. This one is okay. Yes, you got it. Very good. So this is one example. Even the simplest models can appear here. So now let's go like one step further. Okay, and I have like 4 more minutes, so it's very short. No, start too late. So it's also possible to engineer things that are, like Francisco said, models that gauge theories that have dynamical supersymmetry breaking. Okay, and for that, typically, it's useful to use the other tools that this technology allows you to do, which is like a geometric understanding of orientifolds, or a gauge theory understanding of orientifolds. Okay, gives you more freedom how to engineer these things. So this is just an example. I mean, it's a very crazy geometry. It's called pseudo-Pezzo-4. It's a very crazy geometry. You can have these examples in simpler setups. The orientifold action, or the orientifold, it's in dimer models. Even if I didn't explain it, it's related to some involution of the dimer model. Can have some fixed line or fixed points. Okay, so this is an orientifold with fixed points. You need to think that faces that have a fixed point on top of them are like the ones that Francisco was talking about, are gauge groups that are mapped to themselves, and edges that have a fixed point on top of them are things that are chiral multiplets that are projecting to themselves. So these are like two index tensor representations of SUN or UN. And using this example, you can construct this object. It's a gauge theory which has 3 gauge groups. Here things are mapped to the image. Originally you had 7, but then you have 3 UNs and 1 object, which I will call G5, which is either SP or SO depending on the projection, and some matter content which has some 2 index representations. That depends on the choices of the orientifold plane. And it's very much like what Francisco said. It's controlled by some choices of signs. Okay, and in particular, it's possible to engineer the following theory. Okay, this is an SO1 times U5 gauge theory with these representations that, if you looks like a single generation of SU5 grand unified theory. So it's close to the model that Francisco was talking about. So this is one of the models that was originally studied in the 80s. By Affleck, Dyna, and Cyber. This is a model for which you can argue that breaks supersymmetry because it has no flat direction and it has spontaneous breaking of the global symmetry. Okay, so you can engineer these kind of things. Okay, so let me do something else, and then me do something that is more stringy.
Just a provocative question, maybe it's also for later, but in that model that you just presented, what would you say is the scale of SUSY breaking?
Sorry, it's related to the dynamical scale of G5, which yes, G5. Sorry, the U5, which is not G5. Here G5 was SU1. It's related to.
So this is different from the previous examples, where the scale was associated to the unoccupied node.
Yeah, here everything is occupied. Yes. I mean, the guy responsible for the breaking is occupied. Okay, so so let me go more stringy, and I think this is some of the things that I mentioned at the beginning. Sometimes translating, obtaining or engineering these gauge theories in terms of geometry give you a geometric criterion of what the gauge theory is going to do. Okay, so at the end of the day, it will be a gauge theory phenomenon, but I mean, you can have an insight of what's going to happen based on the geometry. Okay, and we are very familiar with the behavior of regular and fractional branes at the conifold. And this is the work of Kleber and van Strassler. We know that they undergo something that is a cascading energy flow, and in the infrared they confine and break chiral symmetry. This is very strongly supported not only by the field theory analysis, but it is strongly supported by the existence of a gravity dual that does all this job. Okay, and you can understand in many ways, but you can understand, for example, the deformation in terms of the geometry, in terms of the gauge theory dynamics at the bottom of the cascade, because it becomes something like an NF equal to NC gauge group, which has a quantum moduli space. Okay, so now, and what happens here is that there's a complex deformation of the geometry, right? The conifold grows an S3 sphere. You have this S2 going to an S3. Okay, so let me say a few words about how the complex deformations look for generic toric geometries, and that's why I discuss these kind of pictures, which are the PQ webs. So a complex deformation in this language corresponds to some decomposition in terms of branes in equilibrium. By this I mean that branes in subwebs such that the sum of all these charges of the external legs add up to 0. So this is an example for the delta of 3, or cone of the delta of 3. You can take all the things that I shown in red, you can put them together, and you can split the web into 2 parts. So you are left, so these things that grow here are like three spheres. These are like conical transitions that you have here, and in this case the remaining geometry is these 2 y's, and this is the way in which we represent the conical here, for example. And if you look at the gauge theory, it's going to do precisely this thing. So one thing that you can do is that you can use all these geometric ideas, and you can classify fractional branes according to the infrared behavior that they're going to have. And there are things that look like Levanov-Strassler that will lead to deformation. There are going to be other things that are called n equals to 2 type behavior. This is when you are left over with some non-isolated singularity where these D-Branes can move. And whatever is the rest are going to produce dynamical supersymmetry breaking by a Fleck-Dyson-Sandberg superpotential. Okay, so let me say one example. I mean, and the question here was whether the Klebanov-Strassler behavior was generic, whether you always get some kind of Klebanov-Strassler, and the answer is no. You can get dynamical supersymmetry breaking. So this example is very interesting because it has a duality cascade and admits fractional branes, and there's even a supergravity solution that describes this process. But nevertheless, the PK web looks like this, and you see that there's no possible way in which you are going to decompose this thing. Okay, and this means really that there's no possible complex deformation here. And the gauge theory at the bottom looks like this gauge theory with some superpotential. This is just a closed version of the 3-2 model. Okay, so this guy dynamical breaks supersymmetry, and it breaks in a way that has a runaway direction. Okay, there's no metastable minimum here, as was originally noted in the original paper, then revisited by some people that went into the details. Okay, very good. So that's so one of the things that, so then what's the message here? Here you have a geometric understanding of where the theory comes from, and already from there you knew that this thing was going to do something which was qualitatively different at the infrared. So next to last example, you can take these models and meta-stabilize them. Okay, so you can take these obstructive runaway models and turn them into something which has metastable supersymmetry breaking by adding massive flavors. Okay, what you are going to do at the end of the day is you are going to cook up something that looks like integrated Cyber-G model. This is not the most the cheapest way of constructing ISS, but it's one way in which you can meta-stabilize these models. And this is, for example, when this gauge group dominates, it's a gauge group which is SU3M with 2M flavors. There's an ADS superpotential that wants to do something. Okay, if you add flavor branes, you have a model which are massive. You have a model with both massless and massive flavors. Okay, and you can tune the number of massive flavors in such a way that you push this theory into the free magnetic range, so you can do calculations there. And I think that the interesting upshot of this idea, not just that you get this thing, is that it led us to study for the first time some cute generalization of ISS, which is one involving massless and massive flavors. Okay, and in order for this metastable vacuum to exist, you need some specific couplings in the superpotential, and these couplings are generated by the geometry. Okay. There are other directions that, if these couplings were not there, would be unstable, and nevertheless they are stable. Okay, and let me just reach the last thing that I want to mention is, again, another kind of models that can appear here, which is the dynamical generated ISS. And this is work that I did with Alberto, with Matteo and Ricardo. Okay, and I mean the original question, I mean, the motivation was that there are very similarities between anti-Brane, Sinclair-Strasler, and ISS. So there was the question whether there was some relation between these two things. I think that the answer is not conclusive, but it led us to think about a cute example that it's also even interesting, I think, from the field theory point of view. So again, we have an orbifold of the conifold, and we engineer this gauge theory, in which we occupy 3 gauge groups, 2 of them with the same rank, and another one with a different rank from the time being, and there's a quartic coupling in the superpotential. Okay? And you can consider the case in which these things are tuned. These numbers are such that from the point of view of the node at the end here, everything is in the free magnetic range. And in the regime in which the strong coupling scale of the first node dominates, this node has an F equal to NC, goes to quantum moduli space, and the quantum moduli space is the following relation. The determinant of the meson minus BB tilde should be here, is equal not to 0 but something that depends on the dynamical scale. On the mesonic branch, what gets is that you get the meson expectation value for the meson, which in this superpotential acts like this. So it's like a mass term for x23 and x32. When do you replace that by expectation value? Okay. So you can think of this. Now you have some ISS here, meaning super QCD with massive flavors where the massives have been generated totally dynamically. And again, for stability of this vacuum, you need P to be equal to M, which is really the bottom of the free magnetic range, even n F equals to 2NC, which has been argued to have SUSY breaking. Okay, so conclusions. Of the 2 talks that we had today, we reviewed gauge theories on D-Branes, both on orbifolds and non-orbifold singularities, and orientifolds. Dimer models are an efficient tool for connecting them to geometry. We saw the effect of D-Brane instantons and the contributions that they do to the gauge theories. And in local D-Brane models lead to a very wide range of supersymmetry breaking theories, and I just showed some selection of them, and I think that it's interesting to investigate them in more detail. So that's it.
Okay, so no questions, no comment, nothing. We are 95 minutes late with the coffee break, so we will have not a 5 minutes, but saying 15-minute coffee break. Sorry for this delay, but it was the first day, so we have to, And we reconvene in 15 minutes. I don't know where the coffee break is. I guess outside here, and they are waiting for us.